All right, so as we first start to explore this idea of parametric equations, a really uh, good example that shows kind of a need for these two equations is an example where we're dealing with two-dimensional motion, right? Single equation just doesn't cut it if we're dealing with two-dimensional motion. So a golf ball, in this example here, is launched uh, with a velocity of 80 square root of 2 feet per second at a 45-degree angle. We want to find equations to represent its path, and we're going to assume no air resistance, which really isn't the reality. There is going to be some effect by air resistance, but that overcomplicates things, so we're going to do it without air resistance. And so what we have to realize is that when we hit that ball, assuming that it's going straight ahead, and we're not talking about left or right, we didn't get a slice on it or anything like that. It's going dead straight ahead. Okay. Then we have both a forward direction and a vertical motion that ball is undergoing. So we have both an X and a Y direction. Okay. So we need to think in terms of what amount of that velocity, that 80 square root of 2 feet per second, how much of that velocity is causing my ball to go up into the air? How much is causing it to go down in the air? And the problem is not as simple as, I'll just do 80 square roots of 2, and I'll cut it in half. Since it's 45, it's equal, right? That doesn't work. That approach doesn't work here. If that was something that you might have thought of. It's actually not going to work. We have to kind of realize, hey, that we're dealing with a triangle here, specifically a right triangle. And if we were to look at this right triangle here at an angle of 45 degrees, we would realize that the velocity could be thought of as the length along the hypotenuse. And then both X and Y then would be your lengths along the legs. And then we can use some trig to figure out what X and Y would have to be. So here with Y, we can say the following, that the sine of 45 degrees is equal to Y over 80 square roots of 2. And so Y would be 80 square roots of 2 times the sine of 45. But the sine of 45 is square root of 2 over 2, or alternatively 1 over the square root of 2. So the square root of 2's would cancel out, and we would get that Y is equal to 80. So that's going to be 80 feet per second. And in a similar fashion, X would be equal to 80. So both of those are actually 80 feet per second. Now, if we do not bring air resistance into effect, then this ball could move horizontally in that X direction, continuing 80 feet every second. Nothing would ever stop it. Nothing would ever stop it. If it was allowed to just move and it was going that way with nothing to ever stop it, then that would be it. It would just be 80 feet every second. Of course, eventually a ball is going to hit the ground, right, which is going to impact it to slow it down. All right. And the friction with the ground and everything. Now, that's our X. And again, this is only going to work until it hits the ground. Okay, so that's a question we're going to have to address in a moment. Okay. Now, what about our vertical part? Well, we've talked about vertical motion before, right? That was with the height. Actually, in Calculus 2, you learn, or Calculus 1, sorry, you learn the derivation of this formula for a falling object without air resistance is 1/2 gt squared plus v0t plus h0. So in this case, my y function would be negative, or 1/2 of gravity, which is negative 32 feet per second, so negative 16 t squared. And then the initial velocity is my 80 feet per second. And in this case, we didn't say, we were just told that it was hit. So let's assume that since it doesn't tell us that it was hit from an initial height, that must mean the initial height must be 0. Okay. And so that would be my y function. That would give me my y value at any time t, my elevation above the ground. Again, that's only going to be valid, though, until it hits the ground. So in this problem, a very important question we need to ask is, how far does it travel before it hits the ground? That will kind of be the limit of our t parameter. Once it hits the ground, this motion that we've described has to stop. It's not going to it's no longer going to obey these rules. Well, it'll hit the ground when y is 0. So we plug in 0, and let's set about solving that equation. So here we can pull out a common factor of 16. So I'm actually going to, just pull out 16 and a t. That'll leave me with a minus t plus 5. So we have two values here. T equals 0 and t equals 5. Of course, t equals 0 is when it started. T equals 5 would be when it hits the ground. Okay, and I just realized I totally didn't pay attention to my question, and I was asking, how far does it travel before it hits the ground? Okay, so not how long it travels, but how far. So t equals 5 is how long it travels. X would be how far it travels. Specifically how far horizontally. Not talking about its length of its path, but rather just simply how far. How far does it travel? So along the ground, it would travel x equals 80 times 5 equals 400 feet. So it travels 400 feet before it hits the ground. 400 feet before it hits the ground. So we could describe the following equation as follows. X of t equals 80t. Y of t equals negative 16t squared plus 80t. And this would be as t ranges between 0 and 5. After t hits 5, everything stops because now it's hit the ground has interfered. What effect that's going to have on the path, both horizontally and vertically, is a whole different story now. It's probably going to roll a little bit further. It'll probably actually bounce a little bit when it first hits, but how much is going to depend on the kind of ground you're hitting. Is the ground wet? So many factors. The temperature of the air, how much moisture is in the air. So many things that would actually contribute to what's going to actually happen there. Okay. So now, one more thing here. Let me just show you how this works. Using Desmos, we can actually graph these things. You can also graph them on graphing calculators. So the way we graph a parametric equation on Desmos is by constructing an ordered pair, and then we type in the variables in terms of the parameter t. So we would do 80t, comma, negative 16 t squared plus 80t, separated there again by the comma, and then close my parenthesis. And you might notice here, it's kind of a little faded, but then they ask us to give values for t, right? And it kind of defaults 0 to 1, right? 0 to 1. So I'm going to go in here and put in 0. And first of all, I'm going to put in 0 to 5, right? And there's the graph. So I can zoom out, right? And you can see here, over time, right, that it comes up and it hits the ground. Now, of course, if you let t go beyond that, this graph will continue, because the graph itself still exists. But the physical reality is once it hits the ground, this graph's no longer going to work. Same thing if you let t be less than 0, it would continue that way as well. We could do such things as that, but it doesn't make any sense, right, in our context of our problem. So one other thing I want to do here, and I think it's worth doing this, is I'm going to replace that 5 with the letter A. And I'm going to say add a slider for A. Because what I want you to notice is as the upper bound here increases, it's going to affect my graph. And so as t increases, my graph is moving from, starting here at the right, the ball is moving from left to right. Right, it's going up, and then it's coming down. Okay? And stop it there at 5. Now, I'll just type in 5, so it'll stop at 5. Okay, so this is something that's new with parametric equations that didn't exist when we looked at graphs for XY equations. And that is that parametric equations introduce a direction of motion. They represent a direction of motion. So here we would mark on here our direction of motion. Our direction of motion. And that direction of motion is referred to as the orientation of the graph. And so we draw those arrows on to indicate as t increases, that's the path that we're moving as opposed to going backwards. Right? So orientation is the direction of motion. Along the curve. As t increases. So whatever way it's moving as t increases along the curve, that's called the orientation. And usually we would describe our orientation either as left to right or in terms of a circular motion, type motion as clockwise or counterclockwise. Is generally how we would describe our motion. Okay, so that is an example of a real situation where we actually do need parametric equations. And it also introduces the idea of a graph of a parametric equation with this feature of the direction of motion called the orientation. orientation.